Hello, everyone. I'm Mohammadreza Bayatpour. I did this paper when I was in my PhD program. I just recently graduated from the Ohio State University. My advisor is Professor Panda, and today I'm presenting our paper on design and characterization of InfiniBand hardware tag matching in MPI. So there is this trend in modern HPC architectures where processors are having more and more core per node. And on the other hand, the network architectures are getting more complex and providing more in-network computing features that needs to be exploited by the middlewares to get the best performance at the application level. Furthermore, modern supercomputers are equipped with accelerators and coprocessors, as well as high-performance storage systems. So pair programming models provide an abstract machine models that can be mapped to different types of the system. So here in this figure, I'm showing you three types of the pair programming models, such as shared memory model on the left-hand side, distributed memory model on the middle, or MPI, and partition global address space, or PGAS. So this research is purely on MPI, and MPI is a de facto programming model for writing parallel applications. And it provides various primitives that can be used by the applications, such as point-to-point operations, which is the communication between the two processes, or collective communication, which is the communication between a group of processes, or RMA operations, which is like remote memory access. So among these operations, MPI tag matching is a crucial aspect to point-to-point operations. And in order to get the best performance at the application level, we need to further enhance these operations in the critical path of the point-to-point communications. For instance, as I'm showing you here, we have this HPC application, and on the line, we have these high-performance interconnects, or it's our hardware, basically. So, and we have the middleware in between, which could be an MPI library. As you can see here, the tag matching is an operation that is on the critical path of the point-to-point operation, and also some of the collective operations that rely on the point-to-point operations, or RMA operations. So tag matching operation is as follows. So in order to realize that the incoming messages are matched with which of the pre-posted receive requests, we need to perform some sorts of matching operation so that the incoming data is correctly placed in the application buffer. In order to perform matching, three parameters needs to be compared to. One is context ID, which is the communicator ID of the MPI application, and source, which is basically the rank of the process which is sending the message to us, and also the tag which is sent, which is some value which is application setting. So MPI operations are based on two different protocols for point-to-point operations. So we have eager protocol, which is mainly used for the small and medium message ranges, and also rendezvous protocol, which is for larger messages. Here in this slide, I'm trying to explain what eager protocol is. So in the eager protocol, MPI library takes advantage of a set of pre-posted and pre-registered pool of buffers in MPI, and then uses these buffers for network operations. Please note that InfiniBand requires a buffer of the host to be registered in order to be used for the network operations. And network operations, such as registration, is a costly operation. And in order to avoid this overhead, MPI libraries take advantage of these intermediate and pre-registered buffers. So as I'm showing you in this figure, in first step, MPI library copies the data from the application buffer to the MPI library's buffer. And then this buffer is registered, and it can be used for network operations. And we have this cost of network transfer, and then there is a copy from the MPI library to the application buffer. So this is how eager protocol is working. As you can see, there is two costs of the copy operation as well as one cost of network. For larger messages where copy operation is costly, MPI library avoids this copy operation and directly registers the buffers of the application. However, as you can see here, this protocol, which is based on the handshaking, has multiple costs such as RTS, CTS, as well as the RDMA transfer, which is basically the actual data transfer, and also the FIN packet. So you see that there are multiple handshakings that needs to happen in order to finish this protocol. If you want to look at the overlap opportunity of these protocols, so basically by overlap, we mean the overlap of communication and computation during the runtime of the MPI application. So on the left-hand side, I'm showing you the eager protocol where we have showing the timeline of the application process as well as the network operations. And we are trying to show that the process is inside which of these phases for both of these protocols. So if you focus on the eager protocol on the left-hand side, we can see that we have the application computation, which is the green part, and at this point, it decides to send the packet, eager packet, to the other process. So all it has to do is to just do a small copy operation, and it is done. And the rest of the things can be taken care of by the network itself. As you can see, there is an overlap of communication and computation here. And at the end, they just need to check for the completion. However, for rendezvous protocol, the overlap of communication and computation is kind of limited. This is because of the various handshakes that needs to happen before the communication starts. For instance, as you can see here, at this point, this process tries to send the RTS. However, the network transfer is not initiated until the time that the receiver process is actually going to the MPI library and progresses the communication and sends back the CTS. So from the start of the send operation until this part that CTS is received, the communication has not yet started, which is leading to lower communication and computation overlap. So all of these challenges and limitations with the protocols in MPI for point-to-point operation bring us to this following. So HPC application requires high performance, low overhead data paths that provide the followings: low latency, it requires high bandwidth and high message rate, and also needs to provide a good overlap of communication with computation. So in order to provide more support to cover these operations, hardware offloaded tag matching is introduced. This is a hardware feature, or basically in-network computing feature in modern InfiniBand network adapters, where you can offload the tag matching operations from the hardware, from the CPU basically to the network itself. So, and we in this paper we would like to see if we can take advantage of this operation in order to get the best performance at the application level. And we would like to see that what are the characteristics and performance of this hardware feature. So let's talk a little more about hardware tag matching and get familiar with it. So basically, this operation offloads the processing of point-to-one operations from the host to the HCA, and it's kind of enables the zero copy MPI transfers in basically both of the protocols. So rendezvous protocol is already zero copy, but the eager protocol, as I discussed before, it requires a copy operation from the application buffer to or from the MPI intermediate buffers. And also it provides a kind of rendezvous progress offload to HCA. So I discussed with you that there are like multiple handshakes in the rendezvous protocol. So using hardware tag matching, we can offload these handshakings and get the best overlap of communication and computation. So basically, the modern X6 or 5 adapters that are providing a new type of SRQ, which is called tag matching SRQ. And this SRQ has the capability of providing tag matching operation inside the adapter itself. So using this new SRQ or shared receive queue, not only the buffer addresses can be posted to it, but also information about the receive request tag can be also uploaded to the tag matching SRQ. So basically the network adapter has those three variables, context ID, tag, as well as the source, that can be used to perform matching operations. On the other hand, tag matching SRQ keeps a limited list of the offloaded tags, and whenever a message arrives, HCA basically tries to search through this queue of the pre-posted tags inside the adapter and tries to find the matching element. And once it is found, it is trying to basically take care of the communication progress and directly write the data to the application buffer. All of this leads to zero copy communication, as well as high overlap of communication and computation, especially for rendezvous protocol. So if I want to draw the different stages of the hardware tag matching for both eager protocol as well as the rendezvous protocol, here I would like to start from eager protocol. So on the left-hand side, as I mentioned, we have this regular eager protocol where we have copy operation, as I'm showing it here. We have copy, we have sending, and we have copy back. However, with hardware tag matching, we can directly register the buffer, send buffer, and we have the communication of the network. And at the end, each receiver is performing the tag matching here and directly writes the data to the application buffer. That leads to the zero copy communication for eager protocol. And for rendezvous protocol, we have the following figure where, so basically without our tag matching, as I said, we have RTS, then receiver has to go to inside the MPI and basically try to respond to this RTS and send the FIN packet. But with hardware tag matching, as soon as the receiver HCA receives its RTS packet, it can perform matching operation, and upon finding the correct value, it can perform RDMA read from the sender side to the receiver side and send the FIN packet to the sender side. So as you can see here, during all of these times, the receiver doesn't need to do anything. It just needs to register the tag with HCI, so that HCI is aware of the pre-posted tags. And during these times, CPU can perform the useful application computation and leave the HCA for to take care of the communication progress. So now let's look at some of the experimental results. So we used Frontera in Texas Advanced Computing Center. It has like more than 8,000 compute node with dual socket Intel Xeon Platinum 8280 or Cascade Lake. And it has a HDR Connect X HCA. And all of our experiments are based on the WebH2X RST2, and the tests are basically with one process per node. So our designs are on the top of the popular MWAPH2 MPI library. It's a very popular library which is used by more than 3,000 organizations, and it is utilized in top supercomputing systems across the world. So first, we would like to look at the impact of zero copy MPI communications for basically eager protocol. As you can see here, I'm showing you the WebH2 performance with and without this hardware tag matching. As you can see, for small messages, there's not much difference, which means that the copy overhead is very limited and we don't see it much. That's why like the performance of the hardware tag matching with or without that, it's similar. But as we increase the messages and we keep the eager protocol, we see the performance improvements. So that it means that removing the copy can be helpful here. On the other hand, you have the rendezvous protocol. As you can see here, the performance is very similar. This one, it is kind of like expected. It's because OSU latency, it's a test where there is no computation in it. So basically, it's a purely communication benchmark. So all the processes are always in the MPI, and there's no opportunity for overlap of communication and computation. That's why the latency is similar with or without Harvard tag matching. However, if we look at the collective level tests, so I'm here trying to show you the performance of the MPI ISCatterV using OSU micro benchmarks. So this OSU micro benchmark for MPI ISCatterV, it has some sorts of the dummy computations, and it tries to see what is the overlap of communication and computation. So it reports both latency as well as the overlap. Here I'm showing you the performance for the total execution time. As you can see on different number of the nodes, like from 128 nodes up to 1000 nodes, we continuously see the improvements with Harvard tag matching, especially for large messages. This is because of the overlap of communication and computation that the Harvard tag matching provides. We also can look at the performance of MPI all-to-all. For MPI IL-12, we also can see the similar benefits. However, as you can see, we are seeing the benefits for smaller scales, like up to 64 nodes, not like until 1000 nodes. So this is kind of expected behavior, because as we said before, the queue length in Harvard tag matching SRQ is limited. And there are a few number of the posted receive requests are there that can be posted to the SRQ. That's why at larger scale, we cannot like post more basically tags to the HCA. That's why, like, as we increase the scale, the benefits also goes down, which is kind of expected. So most probably, I hope that in the future, like in the next generation of the InfiniBand, this queue can be longer so that we can see benefit with the MPI all-to-all at larger scale as well. So here I'm trying to show the basically the overlap of the communication and computation for these two benchmarks that I just showed you. So we can see that, like, for ISCatterV at different number of the nodes, for large messages, there is this good overlap of communication and computation. There is almost like a full overlap because it's close to 100% on different scales. Therefore, we can maximize the overlap of communication and computation and see the benefits at the scale as well. We can see the overlap of communication and computation for IL-12 as well at those scale that I showed you, from 8 to 64 nodes. And this is the reason why we see the performance benefit that I just showed you in total execution time. Because as the communication is happening, network itself can take care of the tag matching operations and provide overlap of communication and computation. We also run multiple applications that I'm showing you here, like from 3D stencil, we can see some good benefits up to 30%. And for some other applications like LAMMPS or NECMON, we could see some few percentages of the improvement. So please note that in order to get more information about the various characterizations that we have done for the Harvard tag matching, please refer to the paper. Due to the lack of time here, I just showed you a highlight of the results. But in the paper itself, we have dense and thorough characterization that can be referred to. So to this end, I want to conclude. So we started with the fact that MPI is a de facto parallel programming model, and it provides various APIs, and Among these APIs, point-to-point operations are vastly used, and it's crucial to have a high-performance solution for it. And one of the major bottlenecks of this operation is tag matching, basically. So in this paper, we try to use hardware tag matching, which is a in-network computing feature to provide the best performance at the benchmark as well as application level. And we analyze multiple protocols in MPI using hardware tag matching and characterize the feature using multiple benchmarks and applications. And this design will be available in the future MVAP2 releases. Thank you very much. Please let me know if you have any questions.